Okay, let's dive right into one of chemistry's most famous mysteries. We're going to talk about a molecule called benzene and the entire family it belongs to, the arenes. And trust me, it's a real head-scratcher.
So here's the puzzle. You look at benzene on paper and you see all these double bonds. Now in the world of chemistry, double bonds are usually like a giant kick-me sign. They're hubs of reactivity, just begging for other molecules to come and react. But benzene, it's weirdly unbothered. It's one of the most stable molecules we know of. So the billion-dollar question is, why?
To really get benzene, you have to meet its family, the aromatic hydrocarbons, or as chemists call them, arenes. These are all ring-shaped molecules that share the same strange, superpowered stability. And benzene, well, it's the founding member, the one that started this whole story.
So how in the world did scientists figure this out? It's a fantastic story of cracking a chemical code, piece by piece, to finally understand what was really going on inside this molecule. You know, the first guess was pretty logical. It came from a chemist named Kekulé, who pictured this neat, tidy little ring of 6 carbons, with single and double bonds just alternating, one after the other. It seemed to tick all the boxes. But here's the catch. If you just nudge those double bonds over one spot, you get a second structure that's just as valid. So, which one is it? Is it structure A or structure B? The weird thing was, the evidence didn't really fit either one perfectly. It turns out, asking which one was the completely wrong question. The real breakthrough was a complete mind bender at the time. The answer wasn't one structure or the other. The real benzene is actually a hybrid, a sort of mashup of both possibilities at the exact same time. It's not flipping between the two, it is both. And this is the secret sauce. Those electrons from the double bonds aren't stuck between 2 carbons. Instead, they're delocalized. They're free to roam, smeared out in a cloud that covers the entire ring. Think of it like this. Instead of 6 kids fighting over 3 cookies, they all decide to share them equally. That sharing, that delocalization, spreads out the energy and makes the whole ring incredibly stable. Now, this special kind of stability isn't just some random fluke. Oh no. For a molecule to be aromatic like benzene, it has to follow a very strict set of rules.
Think of it like a super exclusive club with a tough bouncer. There are 4 requirements to get in. First, you gotta be a ring. Second, you have to be totally flat or planar. Third, you need a continuous loop of overlapping orbitals all the way around. And finally, the real gatekeeper, you have to obey Huckel's rule, which is a fancy way of saying you need a magic number of those delocalized electrons, like 6 or 10 or 14. Benzene, with its perfect 6, is a VIP member. Okay, so what does this super stability mean in practice? Well, it means that arenes are in a class of their own. They don't react like other molecules, and they play by a completely different set of rules. Right, let's put this side by side. A normal molecule with a double bond, an alkene, loves what we call addition reactions. It just breaks a double bond and adds new atoms. Easy. But for an arene, that would be a catastrophe. It would mean destroying that beautiful, stable aromatic system. No way. So instead, it does something much smarter, electrophilic substitution. It just swaps one atom for another, leaving the precious ring completely intact. Because of this, chemists have a whole playbook of reactions designed specifically for arenes. Things like nitration, where you add a nitro group, or halogenation to stick on a chlorine or bromine. There are even clever ones, like the Friedel-Crafts reactions, to add whole carbon chains. But the goal is always the same. Make changes to the molecule without ever breaking that stable aromatic core.
So this incredible stability isn't just an abstract chemical concept. It has massive real-world consequences, and it's a true double-edged sword. It makes these molecules both incredibly useful and, unfortunately, incredibly dangerous.
On the one hand, that rock-solid ring is a dream for chemists. It's a fantastic, reliable starting point for building all sorts of things we use every single day. We're talking about medicines like aspirin, plastics like polystyrene, powerful explosives, even the dyes that color our clothes. So many of them have an arene at their heart. But, and this is a huge but, there's a dark side. The very same chemical stability that makes them so useful is what makes them a nightmare for nature. That ring is so tough to break that living things, including our own bodies, just don't have the right tools to easily take them apart. They're built to last. And that's where the real problem starts. When these molecules get into our bodies or the environment, they tend to just hang around.
And this persistence, this refusal to be broken down, is directly linked to why many of them are toxic. And worse, some of them are known carcinogens, meaning they can cause cancer.
Which leaves us with a really tough question, doesn't it? We have built so much of our modern world on the unique properties of these superstable molecules, but we also know the serious risks they pose to us and to the planet. So the challenge we all face now is, how do we balance the good with the bad? How do we find a way to use their incredible utility while protecting ourselves from their inherent danger? That's the puzzle we're still trying to solve today.